All right, this is Physics 1C for April 22nd. I think today's Earth Day, isn't it? We're going to finish up talking about what we discussed last time with the velocity selector. We kind of got cut off at the end of class. And then we're going to go into talking about a couple other applications of magnetism and forces on charged particles. And then we're going to move into discussing the forces on current-carrying wires. And then we're going to talk about how electric motors work. So that's today's goal, is to get through all those topics. Okay. So last time we were talking about this thing called the velocity selector, and we're going to just kind of briefly go back over what it is again. The idea is that what's up? Everything okay? All right. So the velocity selector is a device where we have, basically think of like a parallel plate capacitor, where you have positive plate over here, negative plate over here. That produces a uniform electric field between the plates that points to the right. And then what we do is we shoot particles through here. And how we do that could be, maybe you have some source right here, okay? You could have like a radioactive nuclei or a radioactive bunch of atoms or something like that have the effect of, occasionally shooting out charged particles with various velocities. For example, some of the things that radioactive particles can decay into are things like alpha particles, which are an alpha particle is like a helium nucleus, which means how many protons are in a helium nucleus? Two, right? And then there's 2 neutrons as well, right? So it has an atomic mass of 4 atomic units, and it has a charge of 2 plus 2. So you could imagine that if some radioactive source was spewing out alpha particles, for example, along with other things, it's also going to spew out beta particles, which are electrons. Then as these particles are spewed out, you can also imagine that due to the way that radioactivity works, because it's a probabilistic process, the particles come out with all kinds of various velocities, basically, right? But let's say you only wanted to pull out only the alpha particles that had one particular velocity for some reason. Maybe you were doing an experiment. You need to like control the velocity of these particles, right? Well, the velocity selector does that for you, because as the particles enter within this regime right here, what happens is that they feel a force, an electric force that goes to the right and a magnetic force that goes to the left, regardless of their charge, right? If I change this particle to a negative charge, then the electric force reverses, but the magnetic force reverses as well. Because remember that what we learned last time was that the magnetic force is equal to the charge of the particle times the velocity of the particle cross product with the magnetic field, right? Remember, B is magnetic field that we introduced last time. So because the charge shows up in this equation, and the charge shows up in the electric force equation as well, remember the electric force is basically just the charge multiplied by the electric field, then the fact that the charge shows up here means that if this is a negative particle, not only does the electric force go to the left, but now the magnetic force goes to the right when it's a negative particle. So no matter, it makes no difference what the charge is, the particles are going to feel forces on both sides like this. Now, depending on what velocity they have, then if the velocity is too small, they're going to tend to swerve off to the right because the electric force is going to be bigger than the magnetic force. If the velocity is too big, they're going to swerve off to the left because the magnetic force will be greater than the electric force. Ultimately, what happens then is if you want to figure out what the velocity of the particles that will fly straight through your detector is, and the idea here is you have some screen right here to block out the particles that don't have the velocities you want. You only want the particles that are going to go straight through like this, along the path where the electric force is equal to the magnetic force. And if you do that, you can find that if the electric force and the magnetic force are equal to each other, magnetic force is QVB, and the electric force is Q times E. You cancel those out, and you find out that this is the velocity of the particles that will travel straight through the detector. And that means that every particle that comes out this other side is guaranteed to have this velocity, regardless of what kind of particle it is. It could be an electron, alpha particle, proton. It could be any kind of particle. It doesn't matter. Every particle that comes out of here will have exactly this velocity, which is really powerful. You can tune specifically your velocity to be whatever you want it to be. And how can you tune it? Well, it turns out that the velocity is related to the size of the field, electric, divided by the magnetic field. And both of these we can completely control. So the size of the electric field, I was saying last time, it can be controlled by changing the voltage of the source right here. So you can basically effectively increase the velocity of the particles coming out if you increase this. So like if I double the size of the voltage of this battery from 9 volts to 18 volts. Maybe I just put another battery in series right here that's also 9 volts. That doubles the voltage, right? Then if I have 18 volts here, what effect is that going to have on the velocity? Remember that there's a direct relationship between the voltage and the electric field that's produced inside of here.
It increases speed.
Increase it by how much?
But if it's another 9 volt, by 2 times.
By 2 times, right? So basically, every time you drop a 9 volt battery in here, you're increasing the speed by 1 unit, right? So if I put another 9 volt battery in here, it's going to be 3 times as big. And yeah, that's pretty powerful. I mean, you can just completely and totally control the speed of things that you can't touch just by changing the voltages here. That's really powerful. I mean, and that's what physics is all about, right? Is about the ability to kind of control and understand nature as we please. So, yeah. Anyway, that's a velocity selector. And we're going to see that this type of object is going to show up in some of the other applications that we use as well. So does anyone have any questions? Okay, so the next application is called a mass spectrometer. Have any of you ever heard of a mass spectrometer before?
Yeah.
Yep.
Okay, and did you hear about it in like chemistry class, biology class, or?
Chemistry.
Chemistry, okay. So let's see if we can describe what's happening inside of this mass spectrometer, and let's see if it matches up with what you've seen in the chemistry experiments that you've done with it. Okay. So a mass spectrometer is made up of, so let's see, let's just grab this, because this is going to be part of it. Okay, so you start off with a velocity selector. Let's put it right here. Okay, so that's the first part of it. Okay, and then what you do is we have this these particles that are coming out of here, and let's give them a velocity vector. So our particles come out of our machine just like this with a velocity. And we know that the velocity of every particle that comes out is going to be exactly equal to the ratio of E over B. Does it come to a surprise to anyone that the ratio of the electric field to the magnetic field happens to have dimensions of velocity? I didn't even talk about that.
That's kind of surprising to me.
This is kind of surprising, right? And we can work it out if we want to, right? Because what are the units? So the units of the electric field would be like newtons over coulombs, right? Or let's use the volt per meter version. I don't know why. Yeah, let's use newtons over coulombs. Okay, that's the units of the electric field, and the units of the magnetic field, I believe, were Newton divided by meter amp, I think. And we'll know very quickly if I'm wrong about this. But I think that's what it was. And again, if you can't remember this, you just go, if anytime you want to figure out what the units of something are, right, you look at the equation, and you say, okay, well, what's B? Well, B is going to be FB divided by QV. Okay, what's F? That's newtons. What's QV? Well, Q is coulombs and V is meters per second. So it's like coulombs per second times, which is amps, times meters. So that's how you can remember what it is. And then you can see pretty easily here that the newtons cancel out, and you end up with like meters times amps, which is coulombs per second, divided by coulombs. And so, of course, you get meters per second. And I do think this is kind of surprising. And it's actually going to be something that is a bit of a hint to where this whole course is going, in a way. It's not just by chance that the ratio of the electric to the magnetic fields is a speed.
Oh.
In fact, there's something to this about the idea that the way in which the electric field and the magnetic field are related to each other has something to do with motion, right? I mean, one of the things that we said early on about this is that when you take magnets and you try to cut them in half over and over and over and over again, you always produce dipoles. And part of the reason why is fundamentally things like atoms that have these charges that are in motion all the time naturally produce magnetic dipoles. Because it's the motion of charges themselves that creates magnetism. Okay? Like, historically, we figured out what magnetism was by finding, like, rocks that could attract bits of metal, right? But now, when we want to produce a magnet, what we do is we use electric currents. And, yeah, that's what the whole next chapter is going to be about. But, yeah. Okay. So, we've got our velocity selector, and we want to describe what a mass spectrometer is. So, we imagine that we funnel all kinds of different varieties of species of molecules or charges or ions or whatever we want into the system, and every one of them comes out with the same velocity here. And then what we need to do is, here, let's take this line. Let's see if it'll let me just extend it. Will it? Yeah, okay. Okay, so this is going to be our detector screen over here. And within the, looks like it says P-tector. Make that a D. So the screen itself is usually in some way like fluorescent, or it has some way of indicating when something hits it. Okay, something indicates when an object hits this screen right here. Okay, and now the next thing that we need is remember that. Okay, I'm gonna remind you what was going on in this picture right here. The crosses here, right? Those represent vectors that point into the screen for the magnetic field. Okay. And what I'm going to do is, within the region where the detector is up here, we're going to put a second magnetic field. And it is also going to point into the page, right? No.
Yeah.
We're going to make it out of the page. Yeah. Okay, so we're going to put another magnetic field here. And this magnetic field is going to cover a very large region. And we're going to have it pointing out of the screen, right? Yeah, okay. And it's going to point out because what I want is for this particle to curve to the right. I want the magnetic force on the particle to point to the right. So here's our magnetic fields. This is going to be a different magnetic field. Let's call this magnetic field B prime. And it's going out of the page, right? It points out. Okay, and we'll just say that it exists in a very, very large region within this area over here. Okay, and now what's going to happen is that this particle that comes out of here, let's say that it's a positive particle. All right. Then a positive particle, when it enters this region right here, what's the direction of the force on that particle going to be if you use the right-hand rule?
It's going to be pointing to the right. Correct?
Yeah, exactly. So you take your hand, you point straight up in the direction of the velocity, you face your palm out, and then your thumb points to the right. So that's going to be the direction of the force. So we have a magnetic force that goes this way on this particle. Just say FB right there. And then the path that it's going to take is going to be circular, right? And I don't really want to try to draw a circle here. So instead I'm going to use an actual circle so it'll look kind of okay. So it needs to be kind of like centered right here. So if I start it up in this corner, we'll call that good. All right, and now I'm going to erase the bottom half of this. Up to like right there. And then is it going to let me, it's probably not going to let me take this object if I do that though. Here we go. This is like the path of the particle now. Hey, look at that, it fits in the field. Now this path will have some radius, right? Oops, didn't mean to do that. This path is going to have a radius that we can call r. And we know that when a particle is in a uniform magnetic field has a velocity v, that if we take the mass times the component of the velocity that's perpendicular to the magnetic field, which in this case is just going to be this velocity, and we divide by the charge of the particle, so q ends up being the charge of our particle here, q, and we multiply by the magnetic field, which in this region we're calling b prime, then that will tell us the radius of this path right here, right? So this particle is going to land right here, and we could very easily measure the distance between this point all the way out to this point right here. And if the radius of the circle is r, then how long is this distance between these 2 points going to be?
2r.
2r, exactly. So we know that basically the place where the particle impacts on the screen and our detector picks it up there's various ways of this happening. It could be a digital pickup, it could be all kinds of different things. We know that distance is basically the diameter of the circular path. And this is really powerful because we can measure this, or your mass spectrometer just measures it for you. We can measure 2r because we can see where it is. And what does it tell us? Well, if we know r and we know b prime, and Well, we know the velocity, right? Because remember, the velocity was equal to... We picked this, right? Because it was coming out of a velocity selector. We knew that the velocity was equal to E over the other magnetic field. The magnetic field, the green field in this region right here. So when we put it all together, what we get is that R is equal to M times the electric field from the velocity selector divided by Q times the magnetic fields in the mass spectrometer area and multiplied by the magnetic field that is in the velocity selector. So there you go. And as I was saying before, everything within this equation is very easy to know. And if we invert it, what we can see is we'll get R times B prime divided by the electric field should be equal to the ratio of the mass of the particle divided by the charge of the particle. So what that means is that the bigger that the mass of the particle is, the longer that radius is going to be. You can think of B prime, and E as all kind of being constants, because we're going to fix these prior to starting to... You would kind of calibrate these, right? You calibrate all of these, you measure R, and what do you know? Well, now you know the mass to charge ratio of the particle. Okay? If the particle has a bigger charge, okay, like let's say it has double the charge, how big is the radius going to be? Maybe you look at this equation right here. Compared to the radius that I drew here, if I put a particle in here that has a charge of 2q but has the same mass, like an ion, yeah, it'd be half as big, right? So you'd get, here, let's see if we can fit it on here and make it half as big. Something like that, right? Right about there. And then we'll just erase the bottom of it again. Yeah, so if I have a doubly charged particle, here, let's make it a different color, like purple or something. And I have that one go into here. This would be the path that a plus 2q particle would have, right? Assuming it had the same mass. So these two have the same mass, right? So really what this mass spectrometer is going to do is it's going to create a spectrum of particles based on their charges and their masses, right? Because the mass is also affected here, right? If the mass is larger, particle has more inertia and it's going to go farther, basically, right? And so you tell me what you see when you actually are measuring things in the chemistry lab, but doesn't it give you like a count or something like that of the number of particles that hit at different points? Doesn't it give you something like a plot like this? Number of impacts per distance in the x direction, if this was the x direction. Isn't that kind of what it does?
I mean, I'll be honest, I don't quite remember it.
You don't know.
I used
That's okay, but I mean, when you've used these before, do you remember, like, did you get like a printout or something like that?
Yeah, it was kind of like a chart.
It was like a chart?
It seems similar to what you just draw right now.
I remember on the y-axis it had absorbance, and then I'm trying to remember what the x-axis was.
Absorbance. So absorbance would be like if something is absorbed on the screen, probably, right?
Yeah.
And if it's going to do anything, it's got to count like numbers, basically. And I think what you're doing a lot of time with these type of things is you're trying to figure out the chemical makeup of a molecule. Am I right about that? Like how many carbon atoms, how many hydrogen atoms, right? And so all you need to do to make it work is to just kind of break up that molecule into some of its constituents, maybe a couple ions or something like that, right? And then, you know, some of the ions will only go so far, some of the ions will go so far, and you can kind of backward solve and figure out, okay, what's the chemical makeup of this molecule now, right? That's incredibly powerful. Like,
That is really powerful.
It's really kind of amazing. Now, one thing I left out of this, of course, is all the particles I'm describing here are positive, but if you have negative particles, they're going to go off the other direction, right? Because they're going to feel the force that's going to flip to the left because they're negative, right? Now, one thing I find really interesting about this concept is that the work that I did when I was in grad school, working on these big detectors where we collide particles together and then we look at the kind of wreckage that comes out of the particles. This is exactly how we figure out what the particles are, right? So the way that the experiment worked is that we'd have, to describe it a little bit, you have these big rings, okay? And the one I was working on, the ring had a circumference of something like 4 kilometers, something like that. And basically what happened is we'd send beams of particles. In one direction, we would send protons, huge bunches of these things, like trillions and trillions and trillions of protons in a big bunch. there's a
You
magnet.
get that many.
Oh, I mean, you just need hydrogen ions, right? So I'm pretty sure we always just use water, and you like electrolyze it or something like that.
Oh, okay.
So you get huge amounts of protons, and then we in the other direction, you send antiprotons. So that's a p with a minus, because an antiproton is exactly like the regular proton, except it has a negative charge. Now, antiprotons are a lot harder to produce. So you may only have 100 or so of these antiprotons, and maybe 1 trillion or so of these protons over here. You get the particles going to a velocity that is extremely fast. It is about 0.9995 the speed of light. That's how fast the particles are going, okay? And at that speed, it's very, very difficult to get them to curve around in a path like this, but they use superconducting magnets to make the particles curve, okay? So the entire track itself is embedded in magnetic fields, which makes the particles curve like this, just like the particles curve up here. And if you don't understand what this velocity means, the speed of light is the kind of maximum speed limit of the universe. Nothing can really travel faster than that. So when you get up to a speed like this, you're effectively at the speed of light for all intents and purposes. So this is like saying their velocity is infinity. Okay, it's not really infinity, right? But it might as well be infinity because that's as fast as you can go in our universe. So what that number is, if you're curious, is about 3 times 10 to the 8th meters per second. A little bit less than that, obviously, because it's not 100% the speed of light, but that's what the speed of light is. That's what c is. Okay, so the particles super fast, and then they impact each other right here at a detector, and there's a detector sitting right here. Okay, and what the detector is made out of, it's a huge detector, is a bunch of toroidal magnets that we have control over. And when these two particles impact each other, you have a matter-antimatter collision. And when matter and antimatter collide with each other, almost 100% of their mass energy is converted directly into energy, okay? Through Einstein's equation that you're all familiar with. E equals mc squared, right? So if you convert 100% of the matter into energy, then out of that ball of energy can basically come anything. Anything that has an energy in terms of its own mass that is less than the energy of the collider can be produced right here. And tons and tons and tons of things are produced. And so you've got to kind of like look at the wreckage of this collision and figure out what came out of it. Okay, imagine that you have like a truck that collides with a Honda Civic or something like that, right? The two things are going to collide with each other. There's going to be all kinds of wreckage. There's going to be broken glass. There's going to be pieces of metal. Maybe there's going to be fire. Who knows? And that's kind of similar to what's happening here. And then what we have to do is we have to look at that wreckage, all the little pieces of glass and stuff like that, and determine what was produced. The way it ends up happening is that particles basically spew out of here. And because they're in a magnetic field, some of them will curve to the right, and some of them will curve to the left. The positive particles will curve to the right. The negative particles will curve to the left. And then what we do is we measure the curvature of the track. Because the curvature is related to this equation. And if we know B prime, and we can measure the radius, we can also figure out the charge to mass ratio, which means that we can then identify what these particles are. So maybe this is a bottom quark, and maybe this is a muon or something like this, right? And so we have sophisticated like electronic systems that go through and tag every single particle. And the goal is to look back at these particles that were produced and see if something more fundamental was produced that we hadn't seen before. Okay, we're searching for fundamental elementary particles, such as, if you've heard of it before, the Higgs boson. That's one of the things we were looking for. But yeah, so this whole concept of the way that a mass spectrometer works, where you take a chemical element and you split it up into its component parts, and then you look at the way in which those parts hit a detector, and then you backward solve and figure out what the chemical makeup of the molecule is 100% exactly what I was doing in grad school. Except the difference was instead of sending chemical molecules through there, we were sending elementary particles and basically being like, what are these things made out of, right? but it's ultimately the same thing, right? I mean, when you're sending chemicals through a mass spectrometer, you're trying to figure out their chemical makeup. You're saying like, I don't know, something you would send through this, right? Pick some organic molecule. I don't know, like propane or something. You want to know what's that made out of, right? And we're doing the same thing, except our question was, what is this made out of? And what is this made out of, right? Because we know that protons are not fundamental particles. They're made out of quarks. And we'd like to understand how the quarks work, because we have a pretty good understanding, but we'd like to know more about it. And we'd also potentially like to produce particles that have never been discovered before, such as, for example, the dark matter, or something called supersymmetry, or evidence of extra dimensions, or whatever. There's all kinds of different things that we look for with these detectors. But ultimately, our only tool for learning anything about things that are this small is looking at the way that they bend inside of magnetic fields. That's all we have. That's our only current method for learning what things are, is we look at how much they curve, and then we use this equation, and it tells us their mass to charge ratio. And that's evidence of what it is, basically, right? What would a neutral particle do? If it came into this region right here, what would a neutral particle do?
Just fly out straight.
It goes straight, right? So that's what happens in these type of systems. Neutral particles are very hard to detect. Very, very, very hard to detect. Because they don't curve. And one of the only ways that we know how to measure things, like I said, is by looking at how much things curve, right? So neutral particles are the hardest. And included within neutral particles are one of the kind of like holy grails of particle physics. And of cosmology, astronomy, of all kinds of different fields. Dark matter is neutral. So what happens in these type of experiments is that if we produce a dark matter particle, it just completely escapes the detector. And the only way we know something was there is we use energy conservation. We say, I know the energy before the collision. These are elastic collisions, so kinetic energy has to be conserved, right? So the way that things like dark matter show up is as missing energy. You sum up the energy of initial, you look at your energy final, and if there's any difference, like if you started with 1,000 joules here, and you end up with only 800 joules when you add up all the energy of all the parts, then either you made a mistake, which can happen, or there's a large amount of missing energy, 200 joules or something like that. And that becomes the type of thing we search for in terms of a signal to find dark matter. And it's literally, the signal is there's nothing there, which is, it's pretty hard in science to convince someone that you've found something new when your only evidence is that you didn't see it, right? Does that make sense why that's hard?
Mm-hmm.
Because if that's your only evidence, is like, oh, I performed a bunch of experiments, and in 1% of my experiments, I had this huge amount of missing energy. So I think that means that we were actually producing dark matter particles, and I can't tell you much about it other than it has a mass less than all this missing energy. Okay, so if your missing energy was always less than 200 GeV, you might say, well, maybe the particle is about 160 to 180 GeV or something like that. It's a very hard problem. It's a problem that I hope that someday we find a better way to answer, because we've been searching for this stuff for like, how long? That's almost like 80 years now. And, we don't have enough statistical evidence to prove that it's there. We don't even know if we've ever produced one. We don't know if we have enough energy in these colliders to produce one. Maybe they're really heavy, and we just need to make a bigger and bigger and bigger collider. I don't know. But we made a pretty big one in Europe called the LHC. They didn't find anything, so now they want to make a bigger one.
Yeah.
And the problem is that the last one they made cost billions and billions and billions of dollars. And it was funded by a lot of governments, including most of the governments of Europe. And it really only found one thing so far, which is the Higgs boson. So a lot of people see it as a failure. And a lot of people in the scientific community do not want to fund another gigantic $1 trillion collider, because the next one's going to cost trillions of dollars.
It's a big project.
Yeah, it's a huge project. And in the United States, we actually produced one that would have been even bigger than the one they have right now in 1995. No, 1992, I want to say, in Texas. It was called the Superconducting Super Collider. It was supposed to be something like about 3 times as powerful as the current biggest collider in the world. And it was going to be... How you just need to close and restart. It's probably just a Discord does peer-to-peer connections over the networks, right? So that means that between me and you, if he can't even hear me, so someone tell him he just needs to restart. Yeah, that's what's happening there. Anyway, so what was I saying? Oh yeah, so these colliders, they're expensive.
The Texas.
Oh yeah, in Texas, it was called the SSC, Superconducting Super Collider. Really cool name. It is just outside of Austin, and they even started building it. One of my dad's friends was contracted to work on building it as well because he was a pipe fitter. Someone that normally works on like oil pipelines and stuff like that, but they needed pipe fitters for this job. And then Bill Clinton, unfortunately, one of the first things he did when he was in office was to shut this thing down. So, unfortunately, it's actually really unfortunate because that would have been in like 1993. It would have been the largest collider in the world to this day. But they didn't want to fund it because it's like, what's the purpose? That's the way they think of it, is like, why don't we just devote all this money that we could put into this into like health research, right? Cancer research, because that apparently has a more obvious kind of application that has a net benefit to society, because the search for particles, it has a more, what's the word for it, esoteric benefit. It's almost like the type of physics. It's almost like the type of physics that we still want to do today. It's kind of similar to pure mathematics, right? Pure mathematics is the study of mathematics where it doesn't need to have any application. It's just mathematics for mathematics' sake, right? Which
You're getting too close to home.
is it? And I'm not trying to hate on pure mathematics. Pure mathematics is amazing.
No, yeah, I totally understand. Yeah.
And the problem is, like, if that's the field you want to go into, there's not a lot of money for it. But the exotic mathematical theories of today are the things that will drive physics and science 100 years from now, right? I mean, it was in the early 1800s that Riemann first wrote down a theory of how to measure the curvature of n-dimensional spaces, right? And n-dimensional space, like, who cares? We live in 3 dimensions, right? Who would want to fund someone that's studying n-dimensional spaces? But guess what? Einstein took that idea and used it to describe the mathematics of general relativity, which completely overturned Newton, right? So who knows, right? If any of you ever end up being the type of people that get to decide these kind of things, just remember that there's a reason why we push forward in science, even if we don't know what the applications are going to be, right? And that's that we're here to discover things. We're here to uncover the secrets of the universe. And we've proven time and time again throughout the history of mankind that even when something seems completely esoteric and seems completely unrelated to the real world and has no applications, sometimes it just ends up changing the world. Like when Maxwell figured out that electricity and magnetism were related to each other and wrote down the equations for it, he probably had no idea that 100 years later the entire world will be running off of electricity, off of the principles that he figured out, off the ideas that he figured out, right? So
that's crazy to think about, yeah.
Right? I mean, yeah, it's you never know where science is going to go, and I think it's best to err on the side of taking a chance, because I mean, we haven't cured cancer in the last 30 years. Doesn't mean we're not trying, but we definitely set back particle physics research for at least 30 years, which is kind of sad. Maybe we would have found dark matter by now. And maybe we would have figured out that dark matter is actually kind of an inexhaustible fuel source that's all around us, or something like that. We just don't know. We just don't know. That's why we keep looking.
So are those particles? It's our only method right now is that it's just missing energy.
Right. That's exactly right. Yeah. Let me show you something real quick. I want to give you an idea of just how noisy these type of collisions are. So when the collisions happen, what's a good picture I can show you? This one's okay, I guess. Let's do this one. This is a pretty good one. So here we go. This is the kind of information that comes out. whenever the collision occurs, okay? Every one of these dark lines right here is a particle. They all just look like lines. I mean, how can you differentiate between them? Well, you differentiate them because some of them are more curved than others. The other information you get comes here. This is the energy and momentum that gets deposited within the collider in different places, basically. But yeah, that's all the noise coming out of there. And you've got to go through and find every particle. And not only do you have to figure out what the particles are, you have to figure out if there was a particle that those two particles came from. Okay, so like you see, I mean, these are the best two that I can think of. This curve right here and this curve right here. These two to me look like they came from a single particle that decayed somewhere back here. And so what you can do is you can reconstruct the mass of this particle and the mass of this particle. And if their masses add up to the mass of something you're looking for, and you get thousands of events like this, then you can be like, there's the Higgs boson. You know, we saw a bunch of situations where we had two particles that had an invariant mass or a total mass of about 120 GeV, and you get enough of those and you're like, well, that's a Higgs boson. Right, so the problem with dark matter is that it doesn't decay. So again, it only shows up as missing energy. So anyway, this is the kind of thing that would show up on monitors every second. There'd be a new image coming up because there are like millions of collisions happening every second as they're taking data. So something that we could not do without computers because it is just an immense, immense amount of data. In addition, they can't even include, we don't even record every single piece of data. The computers only record the interesting events. You have to go and put triggers and stuff in that determine what's interesting. Yeah. Anyway. Okay, anyone have any questions about all this stuff before we keep going?
I heard there's something about the Muon in the news. Have you heard about that?
Yeah.
What is? I mean, so
Can we can you ask that question again after we talk about torque?
Yeah.
So that is directly related to what today's topic is. That's a really good question. But yeah, at Fermilab, which is the place that I was working where these proton-antiproton collisions were occurring, they recently had an experiment, which is an old experiment. It's called the Muon G-2 experiment, where they're measuring something called G, and G is about 2.15 whatever, something. So they measured G-2, so you're just really measuring just the decimal places. And there's a prediction from what's known as the standard model of particle physics of what that value should be. And it is one of the most precise predictions in the history of science. It goes all the way back to Richard Feynman. Richard Feynman was one of the first people to come up with the prediction for what this value should be, based on the way that quantum particles interact with each other, doing all kinds of calculations with what are called Feynman diagrams, if you've ever heard of that. And so the theory predicts one answer, right? And as our methods of detecting things have become more and more and more precise, we've gotten better at measuring this number. And now it appears that we have one of the first ever pieces of evidence of a measurement that deviates from the standard model, which is to say that it deviates from our theory of how particles interact with each other. And I want to emphasize that this is utterly groundbreaking because for 80 years or something like that, this theory, which is one of the most precise in all of science, it has predicted the existence of the Higgs boson, the Z boson, the W boson, all kinds of different particles that were found in the 1980s, the 1990s, the 2000s. Okay? All of these things were predicted to exist in the 1960s. Can you imagine that? You write down a theory in the 1960s. For 80 years, in the modern world, for 80 years, every single measurement that we make only went to make it more verified. Does that make sense? Like you make a measurement, it's like, oh, that's right within the error. And then you make another measurement, you think, wow, this is going to be a little bit off. Nope, right where it should be. Make another measurement, right where it should be. The most successful history in the history of science. Absolutely, without question. Because of the precision of predictions that it makes, combined with the fact that every scientific measurement that we've had has verified those predictions, right? Up until like 2 weeks ago with this measurement of the G-2. So We're going to talk about the torque created on coils, and we're going to relate that to what the G-2 experiment is, and we can just go into more detail about that if you want to. But basically what it tells us is there might be some other forces of nature that we have not. Right now we know of 4 forces of nature, right? Can you all name what they are? What are the 4 forces in nature?
Gravity, the normal force, and then
Not the normal force.
No,
Weak force.
Strong and weak.
the weak force. Sorry, yes, strong force.
the
weak
fundamental normal force.
And then what's the gravity, weak, strong? What's the other one?
force. Electricity.
We got gravity, weak, strong, and electromagnetic.
Yeah.
wait, no.
These two are combined together in the same force, basically.
Yeah,
Now, we've found out that these two are the same thing. The weak and the electromagnetic force. These are the same thing. The weak force governs radioactivity. The strong force governs the forces inside of atoms. And obviously, gravity is what it is. So the question is there a 5th one? And that is what the news would lead you to believe. Now, I don't even know if this is true or not. Because there's so much that goes into this stuff. Like, news organizations have absolutely no scientific, what's the word for it? Skepticism, you know? If there's something that's interesting and they can put it out on a website and they can get a bunch of science nerds like me to click on it, they don't really care if there's any validity to what's being found, right? And if you go through and you look at the experiment that these people performed, it's possible that this is just noise. That this is what has happened so much. I'm very skeptical of any new discovery that occurs until it's been verified by a second experiment or a third, or really 5 experiments or so. Because if only one experiment is seeing it, for all you know, it's a systematic error, right? For all you know, it's an error in the way they're measuring something that's consistently showing up within their experiment, right? Now, the people that did this are all about like scientific rigor and all those kind of things. But again, it doesn't mean anything until someone else can verify it. Because sometimes what happens is that you take a certain amount of data and you observe something and you think, oh, there's something here. We found something, right? And then you take more data and it goes away. And this has happened over and over and over again in the history of science, where people thought they found something new and then they waited a year and all of a sudden they get a deficiency of what they thought was there, right? So if you have plus 10 events, but then over another year you get negative 10 events within that same region, it just adds to 0. It doesn't mean anything, right? So that's kind of where that result is, by the way. People are kind of jumping the gun. As they always do. People just get really excited, and they're just like, oh, look, there's a new force. What could it be? And I guarantee you, if you were to go onto any of the servers where they publish papers and stuff like that, that there has been a deluge of papers that have been written about this result, you know? Because that's just what the community does. They just, you know, there's a new result, start writing papers about what the reason why that happened is, right? That's just what they do. Otherwise, they just sit around and write papers about nothing. But as soon as they have a result, they'll be like, oh, we can make a theory that will fit that experimental evidence, right? And if they're right, you know, great, but most of the time they're wrong. So, and then what I think is really funny is when they come up with this theory, right, that's supposed to explain what they've observed, and 2 months later, the people doing the experiment tell you that the effects went away. You know, so then they spent all this time writing down this amazing theory that explains what was seen, and then the experimentalists are like, "Well, actually, guys, sorry, we made a mistake." It's really funny. It's really funny, and that's. I swear to God, that's like the last 60 years of particle physics. Nobody knows what's going to happen because nobody can write a better theory than was written in the 1960s. Just think about that. How annoying is that? That some scientists in the 1960s, some of them are still alive today, actually, they wrote down a theory and nobody can do any better for 80 years. And we're talking about hundreds and hundreds of people that have gone through this field, thousands of people, really. I mean, there's probably like 8,000 people working on the current experiment in Europe, between professors, postdocs, scientists, grad students, accelerator physicists, engineers. There's thousands and thousands and thousands of people working on these experiments, and no one can come up with a better theory. It's really funny. We got a lot of good candidates, but we haven't found evidence for them yet. Okay, there is one other type of application, which is called the cyclotron. And if I can get through the rest of the topics from today, then we'll talk about the cyclotron. But I don't know all the time. We can always do it next time. All right. So the next thing that we want to do is we want to talk about the force on... Oh, we have this problem we can do now, actually, and then we'll talk about the force on. Okay. So let's look at a problem that is related to what we just did. Here, let's put this on the other slide, too, because that's going to be connected to the mass spectrometer. Okay. All right, so here's the problem. Okay, so there's almost no helium in ordinary air. So helium sprayed near a leak in a vacuum system will quickly show up in the output of a vacuum pump connected to such system. So you're using a leak detector that uses a mass spectrometer to detect helium plus ions, which have a charge of positive E. So if it's a positive ion with a 1 plus, that means it has one extra positive charge. So it basically means it's missing one electron. And they have a mass of this. Ions emerge from the velocity selector with the speed of this. They are curved in a semicircular path by a magnetic field B', and they're detected at a distance of 10.16 centimeters from the slit S3 in figure. Okay, so that's going to be, for our picture, it's from here. From the slit, we want to calculate the magnitude of the magnetic field B'. So basically what we want to do is take this type of a system right here, where we've been given the velocity, and we've been given the charge and the mass, and we also know something about the radius. So basically we know everything we need to know in this equation right here. And we want to solve for the magnetic field. Pretty easy calculation, honestly. Right? So our goal is to solve for B'. Now it says that they are curved in a semicircular path and are detected at a distance of 10.16 centimeters from the slit. Now let's figure out what that is. So if it's 10.16 centimeters from the slit, then what is that going to be equal to? That's this distance right here.
It's 2r.
So this is 2r, right? Okay. So the value that they give us is 2r. So that means that 2r is equal to, what was it? 10.16 centimeters. So that's going to be 0.1016 meters, which means that r is just half of that, which should be, what, like 0.0508, I think, meters?
Yeah.
Okay, so if that's the radius, and we know other pieces of information, such as we know what the velocity is, so that's v. Let's use a color you can actually see really well. I didn't switch it. Switch. So our velocity is equal to 1 times 10 to the 5. And the charge is plus E. And then the mass is 6.65. Okay, so basically we just need to plug all these things in this equation and solve for B'. So B' is going to be mv over qr. So it's going to be times, and then divided by the charge, which is 1.6 times 10 to the negative 19. And then this is multiplied by r, which we said was 0.0508 meters. And now we could kind of check to make sure the units here work out. So what do we have? We have kilogram divided by coulombs times seconds, right? Mm-hmm. Kilogram, meters cancel. Yep. Okay. And then what do we get for the number?
8.18 times 10 to the negative 2.
So 8.18 times 10 to the negative 2.
Maybe someone should...
Yeah, see if anybody
put something wrong.
Let's see if anybody else gets the same answer. Let's see, 27 plus 19 would be 8. Negative 8. Negative 8 plus 5 would be negative 3. It seems reasonable to me, because then this is 10 to the negative 2, so... Order of magnitudes wise, that looks fine. Anyone else get the same answer? So kilogram per
I got the same.
coulomb second. Let's see, so Coulomb, this is tough, but basically we need to change, so coulombs, if I multiply by, if I do coulombs per second times seconds times second, that doesn't change anything, right, for the denominator? And then for the numerator, if I go kilogram times meter divided by meter, that doesn't change anything, right? So then that gives us, looks like kilograms times meters per second squared divided by coulomb per second, which is amp. And then I have another meter that's left over here, just kind of rearranging the stuff that I did here. And that is the same thing as newtons divided by meters times amps. And of course, that is being written in the area where you can't see. Sorry about that. So that's Teslas, right? Newton over meter amp. So we get 8.18 times 10 to the negative 2 Teslas. And I'm just going through the units there because these units from electricity and magnetism can be a little bit confusing sometimes. Okay, you have any questions? So I guess this is a kind of problem where maybe you could use the information that you have here to calibrate your magnetic field, perhaps. But the reality is that normally what happens, this is the way that university physics loves to do things for some reason, you'd actually probably be using such a device not to figure out what the magnetic field is, but more likely to figure out something like the charge to mass ratio. But anyway, it's a decent problem nonetheless. Anyone have any questions? Okay, we need to take a break. So let's take a break. And then when we come back, we are going to talk about the force on a current carrying wire.